Now let's proceed with housing technologies. So that mainly means to make packages for first level and second level integration. And for first level integration, we will have a look at what has happened between, let's say, 1960 and today. In the beginning, we had very simple transistor housings, like here, that typically was a so-called TO, transistor outline. After the IC was invented, for instance, a 4-bit microcontroller, we had a so-called dual inline package, DIP. And around the year 1980, that means, let's say, after 15 to 20 years of having such devices which were still soldered into holes in the printed wiring board, so-called surface-mounted devices were developed, and the technology is surface mount technology. And here we first had devices which have only on two sides the IOs, or they have IOs on all four sides. These devices are just put on top of a printed wiring board on the solder pads and are soldered there. On the other hand, the requirements to have larger and larger I/O numbers led to the invention of the ball grid array. We must say before that we had the so-called pin grid array, so the pins were removed, the balls were installed, and then we had such ball grid arrays. In that case, it's a flip chip ball grid array because the chip is mounted by flip chip technology on the ball. What we have here is, for instance, a multi-chip module, BGA in that case. The individual chips are interconnected by wire bonding. We also found, after the year 2000, stacked chip BGA, so that means chips on top of each other, but the restriction here was that the higher chip must be smaller than the lower chip. Okay, in that way, packages became more and more complex, and what is also important is that these complex packages also took over some of the functions of the second level packaging. So it was a trend toward integration where the strict distinction between first level and second level packaging was no longer existing. But first, let's have a look at the first revolution that was going from a dual inline package, which is just installed in the printed wiring board here. We have something which is put on top, and here we have the solder joints, or in the case of a ball grid array, we have the solder balls. If the legs of the device are more like the Dachshund legs, it's a so-called SO device, or the alternative is a solder ball. What are the advantages of that technology? When you have more and more IOs, you must make the pins smaller and smaller, and you have 100 pins in parallel. Now imagine all of the pick and place is done in an automated way. Yeah? You must have a machine which puts your device into the printed wiring board. And now imagine you have 100 very flexible pins, and one pin is bent only a little, and you want to press it with an automatic machine into these holes, then you will have a big problem. And in order to avoid these mechanical problems with through-hole technology, surface-mounted technology was invented. Another aspect was that the pitch of the I/Os could be reduced significantly. So you have easier manufacturing, easier pick and place, and smaller pitch. What is the pitch? That is the pitch. And in that way, it was necessary to do the transfer from through-hole packages or through-hole interconnections to surface mount technology. Another thing which is important and which had been in use was reactive transfer molded packages. Such packages always consist of a lead frame. That lead frame is made of copper, and onto that lead frame a chip is mounted, and that is adhesive bonded. And after we have that, we need wire bonds. And in the end, all of this can be coated with a plastic material, and so the device is almost finished. That technology is both for through-hole technology and for surface mount technology. Okay. Again, we see here our Micronas Hall sensor, which is a very good example of such a device. That device is very complex. I already explained it, so I don't have to go into the details. But having such very precise device requires, we need the Hall plates, we need analog digital converter, we need digital signal processor, we need a digital analog converter, we need an operating amplifier, then some information. For instance, the calibration curve is in an EEPROM, and there are other things which are important. For instance, the AD converter requires a band gap reference, so we need a very precise voltage reference which is independent of temperature. And we need also a temperature-dependent bias, because the conductivity and the mobility of the carriers in the Hall plate is strongly temperature-dependent. All of this at costs of maybe €0.50 per device or so. Okay, here we see a cross-section. First of all, that's the device on the lead frame, and that would be the device after it is molded, after the leads have been tin coated, and after we have laser written some data on top of that device. Here we can see a cross-section. That here is a copper material, that is the silicon, and that here is the molding compound. What is a molding compound? We will see it in detail. It is a plastic material which contains some filler. The fillers we can see here, it's these small dots. It's, you could say it's nanometer pebbles. And pebbles is typically silicon oxide. With such technology, we can make through-hole packages which start from dual inline shrink. That means smaller, we have a narrower dual inline or slim dual inline package. Then for power transistors, we have single inline packages. The most, let's say, simple is something like a TO220 or such a thing. And if we have more IOs, we can also have a so-called zigzag package, which has 2 layers of the pins. Again, here that devices is just installed into a printed wiring board. And the heatsink must be somewhere else, like it is here. What is also a device which is for high I/O numbers is a so-called pin grid array. Here we already have an array of IOs, but these still are pins, and typically such PGAs are put into a socket. Maybe 10 years ago or so, typically AMD processors were pin grid arrays which we put into some socket. On the other hand, making the device smaller and bending the IOs like the legs of a dachshund gives us a surface-mounted device. Then the next step was new, putting these IOs on all sides of the device. You can bend them outwards, you can bend them inwards, then it's a leadless leadless chip carrier, you could say it's out of date. And then we have PLCC, which is again a similar package. What is important now is more the BGA and the chip scale package, which can be a small BGA or which is a small package which is similar to a BGA. In that way, we can see not everything was new in the first level packaging, but many surface-mounted devices were just modifications which were drawn from through-hole packages. How do we produce it? The first step, we start with a lead frame. That lead frame can be bent, but normally it's flat. On the lead frame, we put some adhesive. That adhesive is typically printed in some way. It can also be inkjetted. We put on the adhesive. Then the chip is mounted. We call this also pick and place. And of course, no person will do this, but this is done by an automated system. And after we have this, the lead frame is put in an oven and at a temperature between 100 and 200 degrees centigrade. The glue is cured. That depends on the type of the glue. At the next step, we can go into the wire bonding. The wire bonds are drawn from the chip surface to the lead frame. What is always important is that the chip has a passivation. So the circuit is protected by this passivation, which can be an oxide or nitride, and only in places where we want to wire bond, we have a metallization. And now what is the metal? It is typically an aluminum alloy. We will see what it is. And after we have accomplished this, we put that lead frame into a molding machine, and in that molding machine we inject some molding compound, and here is the molding compound. After that, typically the leads are bent again, and they are electroplated with tin, for instance, and in that way the package is finished. That's such a molding machine. You could say, yeah, what's the principle? It's similar like the iron my mother used for making waffles. Yeah, waffles are between two structured iron plates which are heated. You put in some material and close it, and then the waffle is hardened, and when it's brown and crispy, you can take it out. And molding is very similar. In that case, you have a molding machine that are the heating plates. Here, a lead frame is installed. With the pre-assemblies. So then the whole thing is coated, and on top in some way the molding compound is fed. Then we have a piston which presses the molding compound into the cavity of that heated tool. Which has a cavity. The liquid molding compound will run into this mold or into that heated tool, and it will immediately harden. We can see it here in more principle. We have the top side of that heated tool, we have the underside. Here we have the IC chips on the lead frame which were pre-assembled. On top is the transfer pot. The molding compound is placed inside that pot, and then a piston presses it. As the temperature is quite high, for instance, the temperature is let's say roughly 165 to 180 degrees centigrade. This molding compound becomes liquid. It will be pressed along these so-called runners. And it fills the cavities around the chips, and in that way the packages are formed. So that means the packages are still together on a lead frame, and after that the lead frames are taken out. The leads are cut with some automated tool. They are bent in order to form through-hole legs or surface mount device legs, and so devices are produced. The time in such a machine is typically 1 to 2 minutes of hardening to harden, and maybe 1 to 2 minutes to feed and to take out. So, and to reload. That means that process can be quite fast, and with that process we can produce tens of thousands of devices, if they are small, in just one shot. Here is again a cross-section of that machine. We can see here the cavity. Here are the so-called system carriers. That's the lead frames with the chips. They are put in. Of course, you cannot put them in by hand in a tool that is 180 degrees centigrade hot, but these are pre-arranged on some magazine, and that magazine is fed. So you feed them all together in, and then this waffle iron is closing. The piston will shoot the molding compound into the runners. The material will be liquefied, and in that way it is filling the cavities, and after the cavities are filled, this material hardens within a minute or so. Okay, in that way the devices are produced, and let's say such small outline packages were just the first step. But here we would like to have a look at more complex devices. Let's start on the bottom. The bottom would be how can we develop this technology? One idea was to mount the chip directly onto the lead frame, and at the same time not only make the mounting of the chip, but also make the chip topside interconnection. Then put that whole device into the molding machine, and either to selectively or to generally mold it. So that is a chip scale package, but it uses normal lead frame and molding technology. That is important because often companies have their equipment and they would not like to change all of their equipment, but they would like to keep a technology which they know, where they have the machinery, and then the easiest is just to change the design of the devices and not to implement a completely new technology. Something new would be the chip scale package, which is made as a ball grid array type. Here it's quite different. We have a printed wiring board. Again, on the printed wiring board, we do the pick and place of the chip. We glue it. We wire bond it. And finally, we mold it. Again, many steps of the traditional technology are preserved. So we have no lead frame, but a printed wiring board, but we have wire bonding, we have the gluing, we have the wire bonding, and we have the molding. Other companies had other ideas. One of the reasons is that you don't want to pay for patents of other companies, so some companies design their own package. For instance, we have the silicon chip here, then we just take a foil which has the balls, and that foil is attached here to the chip. That is a so-called fan-in micro BGA. Fan-in means we come from the outside of the chip to the inside in order to make these interconnections. And I think that's not so important. These two types are really important. And just to show you the examples, here is such a lead frame type. Here we can see clearly the lead frame. Here is the molding compound. Here is the wire bond. On the other hand, here, that's a device, that's the IC, and that already is the printed wiring board. Here we see this ball grid array we had on the previous page in a cross section, and that here is the so-called fan-in BGA as we have seen it. These two are finite element models in order to show the construction and to do a simulation of that device. But we have more. Some people thought, why molding? We just put the chip as a flip chip on top of that printed wiring board carrier. That carrier is also called interposer. And no molding compound, but the backside of the chip is strong enough and the chip is thick enough, so we do not need any protection. The chip protects itself. Okay, I would say that device is in limited use, and a completely different design was something where we had a complete wafer, and the complete processing is made on the wafer. Here we have the silicon. The silicon wafer is mounted on a polymer. Then we can etch trenches in the silicon. We can put on a front side polymer. We can process it, and in the end, it is just sectioned. That seems to be very, let's say, convenient method, also very effective, but in the end it is not desired so much, because here is lost silicon. And that is something which is not desired, because loss of silicon means you lose the number of chips. Yeah? Maybe it can be 1% to 5% less area that can be used for active silicon, but it is some silicon which is expensive, but it is just processed and then etched away. And so nobody in a fab wants to lose just 1% of silicon, and that's a disadvantage of such packages. So that's one of the reasons why we do not see so many of these wafer-level packaged chips. You can make very small devices. The size of the device is only a few % larger than the chip, but on the other hand, production is not so efficient, and that's a disadvantage. Okay, so we have seen something like that, and that's one of the reasons why such QFN, quad flat, no lead, based on molding and based on lead frame technology is so successful. Until the year, let's say 2000 and a little, it was not possible to make cavities here, and so these molded devices were not suited for sensors. But since that time, some innovative companies, they found a technology how to preserve this open hole on top of the chip in the molding process. That's not as easy as it might seem to you. And after that, such sensors were made possible. In the end, such technologies, one is ISC integration of sensors, and the second is innovation in packaging technology, led to new companies like Bosch Sensortec or Sensirion AG. In fact, quite many people studying here in IMTech worked with Sensirion, which is a very innovative Swiss company. Here is another thing which I already mentioned. It's a so-called system in package. You can stack chips, and just by using wire bonding, you use again an interposer. You glue the chips on top, so it's a typical wire bonded BGA. On the other hand, here we see the molding compound, and in that way, for instance, some companies like Infineon could produce big memories where you just increase the gigabyte number just by stacking the chips. So that is also something which is possible and which is a quite recent development in such molded packages. Okay, now let's have a look back. When we look at the development, let's start with quad flat pack. As we saw it, we have a pitch of 0.8 millimeter. On the other hand, if we would say we just put the chip on the printed wiring board and we wire bond it, it is called chip and wire. We have a pitch of roughly 0.2 millimeter. If we have a flip chip, for instance, we would have on a printed wiring board, we would have a pitch of 0.3 millimeter or lower. On the other hand, when we use chip scale packages, either with carrier or with interposer, we can go down to 0.5 millimeters typically in such a micro BGA, or when we use a wafer level surface mounted device, we can go down to 0.2 millimeters. So in the end, having modern package technologies for chip scale packages, the pitch we can achieve is in the order of magnitude what we can achieve with chip and wire and with flip chip technology. In the end, people processing printed wiring boards and making second level integration, they prefer devices in a package. They do not like to deal with bare chips like chip and wire or bare flip chip. So generally the trend has been with especially such devices in the recent year, while the starting point was the quad flat pack. For the other devices, we will see in later phase of that lecture. Okay. Reactive transfer molded packages were initially just made for standard packages. But some would like to have more. And one thing is to integrate sensors into package sensors. And one of the things is, could it be possible not only to make a hole on top of the molded package, but to attach something? For instance, we want to attach some tubing, for instance, for pressure measurement, or if we have two such things, we can make a flow sensor and such similar things. Another thing is, can we implement on the lead frame in such a device something like a bearing? Yeah. In the bearing, we could integrate a shaft. That shaft is rotating, and the rotation can be measured by a magnetic sensor. Yeah. For instance, counting bits when we turn it, and in that way, we could make a very efficient package. Yes, we mount this package on a printed wiring board. That board, of course, also has a hole. And the complete system is very simple. It is large series production, where we talk about millions of devices which are produced. And such things are possible now in molding technology. In the end, such developments of innovative molded packages were not the result of Far East companies, but it was a result of smaller companies here in Europe. And in that way, we can also bring back some of the production back to Europe just by having innovative devices. So again, here is the simple molded package based on lead frame. That was how it started, but that's the basis for understanding of such technology. Okay.